Oh, okay, good. So I finally got that to go. All right, so this section is about absolute value equations and inequalities. All right, and so here, remember the absolute value of a number is defined to be its distance from 0 on the number line. So if I gave you the absolute value 5 would be 5 because it's 5 units to the right of 0 on the number line. Similarly, the absolute value of -5 is still 5 because it's 5 units from the origin on the number line, right? Even though it's to the left, it's still 5 units away from the number line. So the absolute value is a distance, right? So in particular, let's take a look at this your turn, right? So you want to think of equations involving absolute value of an unknown. So for this guy, when we're looking at the absolute value of x equals 19, you want to ask yourself, what real number or numbers, if any, are 19 units away from the origin, right? Well, we already know you can go 19 units to the right to get 19, or you can go 19 units to the left to get -19. All right, and so there would be two solutions to that one, 19 and -19. For this guy, the absolute value of a real number is -5. Well, by our interpretation of absolute value, it's a distance, and we know distance cannot be negative, and so there could be no real number whose absolute value is -5, so it has no solution. And then finally, this guy here, the absolute value of x is 0. What real numbers are 0 units away from the origin? Well, there could only be one. You couldn't have ever moved away from the origin to get that number. So the only solution to this is 0 itself. For example 1, if we can somehow write an equation involving an absolute value of x or some expression involving x in this form, the absolute value of something equals a number, then we can use the previous principles up here, these three cases, to get rid of the absolute value, right? To actually tell us what these solutions have to be. And so for instance here, if I want to rewrite this in this form, all I have to do is add the 5 to both sides to get the absolute value of x equals 13. And then we know from above, since this is positive, right? Since that is positive, the two solutions to that equation would be 13 and -13. Okay. For this your turn, we'll just kind of talk about it since it's basically the same. Subtract 4 from both sides to get the absolute value of x equals 1, and then we know -1 and 1 are the solutions. What we want to be able to address is this in general. So if I have the absolute value of some expression equaling a number, I want to get rid of the absolute value, right? So I'm going to have these three cases. One, if c is negative, right? So if you have the absolute value of something on one side and a negative number on the other, there's no way there's going to be an x value for which that's true. So immediately, without doing anything else, you know there is no solution. If that number is 0, the only way the absolute value of that expression can be 0 is if the expression itself is 0, right? So you can get rid of the absolute values and just set the inside equal to 0 and solve for x, using whatever method you have at your disposal, be it a quadratic equation, a radical one, a rational expression, who knows? But once you get rid of the absolute value, you can solve that using what you already know about. And then if the c is positive, that's where there's more work involved. Then you have two equations that have to be satisfied, namely the inside equal to the number and the inside equal to the negative of that number. And you solve those two independently of each other. All right, so let's look at the equations in example 2. All right, so the first one here, remember, I want to try to get these in the form of the absolute value of something equals a number. Right, so here I want to get rid of the 3. Don't multiply through by the 3. These aren't parentheses. These are, the absolute value indicates a function that does something to that input. So don't treat them like parentheses, right? I'm going to divide both sides by 3 to get absolute value of x plus 4 equal to 3. And now, since that right side's positive, what I'm going to get is two equations, right? I'm going to get x plus 4 equals 3. So that's the inside equal to 3. And the inside equal to the negative of 3. and you solve both those independently to get -1 and -7 respectively. All right. So one key thing that I set up here is that don't treat the absolute values as parentheses. Moreover, you can't distribute the absolute value through a sum. So a lot of times people have the temptation of saying that the absolute value of a sum, like x plus 4, is the absolute value of x plus the absolute value of 4. Can't do that, right? If everything is positive, it works, but you're eliminating the possibility that x could be negative, and in that case, this equality would fail miserably. So just be careful. You cannot distribute an absolute value through a sum or difference. All right. For number 2, you have the absolute value of something already equals 0, right? So from the previous case, we know that the only way that can be satisfied is if the inside itself is 0. And so I get 7 minus 2x equals 0. If you solve that for x, you get 7/2. All right. The next one, we almost have it in the right form, but we want to get that 3 on the other side. And so I'm going to move it over, right, to get the absolute value of -1 minus 2x, that absolute value of that whole thing equals 21. And then I'm going to set the, oh, hold on, my dog wants it. Hold on one second. Go. Sorry about that. Okay, so you set the inside here equal to 21 and the inside equal to -21. And then you just solve those linear equations like you normally would. Okay. And then finally here, you have the absolute value of 2x or 2 minus x squared equal to 1. And so we set the inside, notice the absolute values are now gone. We set the inside equal to 1 and -1. Those are two quadratic equations. So you have to use whatever method works for solving a quadratic here. Since there's no strict x term, we're going to go ahead and use a radical method, which means I'll get the x squared on one side by itself, the constant terms on the other, and then take the square root of both sides, realizing that when you do that, you get a plus or minus each time. All right, and so I get x squared equal to 1. That means x is equal to plus or minus √1, and then the same way over here, so that in the end, you actually get 4 solutions. All right, so go ahead and try your turn 3. Same sort of idea. You want to write these ultimately in the form of absolute value of something equals a number. And then depending on if that number is positive, 0, or negative, you have one of 3 approaches that you have to take to get rid of the absolute value bars and then to solve for x. All right, so take a minute, do those, and then I'll put the solutions up on the screen momentarily so you can check yourself, but make sure you pause before you do that. Okay, so let's take a look at them. Notice again, here, I don't want to distribute that -5 through the absolute value. Nope, I want to get the absolute value term on one side by itself, a number on the other. And so I'm going to subtract 4 from both sides, and then I'm going to divide by -5. Right? If I do that, I get this equation. That number is positive, and that means I want to set the inside of the absolute value bars equal to that number or to its negative and solve those linear inequations that result. This one's already in the right form, right? So I can set the inside equal to 16 and the inside equal to -16, solve those equations directly to get the 2 solutions. This one is a little bit trickier, right? Because now in order to get the absolute value on one side by itself, you're multiplying both sides by a negative number. And so you get this. Don't immediately leap to saying that the 3x has to be -5 and the 3x has to be +5. That does not work here, right? Stop and think about this before you go ahead and do that. There's no way an absolute value can be a negative number, right? And so this equation has no solution. Okay? And then finally over here, if you want the absolute value of something equal to 0, the only way that can happen is if the inside itself is 0. So that yields a quadratic equation. This one can be solved easily by factoring out an x and then setting each factor equal to 0 and solving. All right. The next thing you want to look at are absolute value inequalities. And we're only going to look at the linear case in the here because the other cases are a little bit more involved and they really don't come up that often in Calc 1 or 2. And so I'm just going to omit anything but linear absolute value inequalities. All right, so let's go back to the notion of a distance, right? If I want to interpret the inequality absolute value of x less than 3, what you're always doing in this form of an inequality is you're starting at the origin and you're saying what numbers are no more than 3 units away from the origin. Well, I know I can push up to 3. Any number strictly less than 3 between 0 and 3 would work. 3 itself doesn't because x is equal to 3 there, not less than it. So I'm going to put an open hole there on a number line to signify that that does not satisfy the inequality, but everything in between does, right? So I'll shade that in. And now I can do the same thing on the other side, right? I can move 3 units to the left of 0, or just adjust up to 3 units to the left if you want. Everything between 0 and -3, not including -3, works because its absolute value would be less than 3. And so everything actually between -3 and 3 would be a solution to this inequality. All right, and so the way we'll write that, you can rewrite the absolute value of x less than 3 as what we call a double inequality. It's simply an inequality that involves 2 comparison symbols, right? And they notice they're going the same way. You can't have less than on one side and bigger than on the other. That doesn't make any sense, right? So make sure that the inequality signs are both going in the same direction. All right, if I happen to have included the 3 here, so if this were absolute value of x less than or equal to 3, then the only difference would be I would have shaded these guys in, right? So I would have included 3 and -3 here, which means I would have had an equal sign on each of these guys. And so the result wouldn't have been an open interval, it would have been a closed interval, right? That's the only difference. Let's go the other way, right? So if I want all the real numbers whose absolute value is larger than 3, now you want to be at least 3 units away from the origin. Not at most 3 units, at least 3 units. So the first, you'd still use 3 as your boundary point. 3 does not work because 3 is exactly 3 units from the origin, but any number to the right of 3 would work. And similarly, any number to the left of -3 would work, right? So here we're going to get the tails, if you will, of the number line that satisfy this inequality, okay? And the way you write that, you have 2 disjoint rays. A disjoint means they don't overlap, and they're rays because they extend off to plus or minus infinity. And so the way we'll write that, we'll write each one as an open interval, right? This guy is the first one, this guy is the second, and I'll write a U in between for a union, okay? All right, so let's look at this. So just typical sort of starting examples like we did for the equations. If I want to interpret this inequality on the number line, this means that you want all numbers that are less than or equal to 6 units away from the origin. So I can push as far right as 6 and as far left as -6, and everything in between those 2 guys, including, would actually work, right? So you get this solution to that inequality. For this one, let's interpret it verbally. You want all real numbers that are whose absolute value is positive. All that means is that the number is different from 0, right? It has to have moved away from the origin in order for its distance to be positive. And so here, the only real number that doesn't satisfy this would be 0 itself, right? So all negative and all positive numbers would actually work. And then here, can there be an absolute value of a number that's less than -2? Well, to be less than -2, it would have to be negative. And we've already said the absolute value of anything is non-negative. So this would have no solution. All right. So using those cases as a guide, I want to talk about these absolute value linear inequalities. If the C is if the C is a positive number, right? You want here, you remember the interpretation was that you want the numbers that are at most C units from the origin, you get this double inequality. Negative C on one side and C on the other. And so what we're going to say is that if you have an absolute value of a linear expression less than C, that's going to be equivalent to this double inequality, right? That's important because I have to get rid of the absolute value before I try to solve the equation. You can't just distribute an absolute value or just get rid of it some other way. You have to get rid of it in a way that uses its meaning, its definition in terms of distance. All right, so whenever you have an inequality of this form, you immediately transform into a double inequality. And then to solve this sort of inequality, you subtract the b from all three places. So subtract the constant that's in the middle from everything. And then you divide all pieces of the inequality by the coefficient of x. If that coefficient of x happens to be negative, remember to reverse both of the inequality signs. All right. For the other direction, if the inequality happened to be larger than C and C was positive, then remember there you're getting the tails, or you're going to get the two rays. And so the inside itself could be to the right of C, or the inside itself could be to the left of negative C. But to the right of C means bigger than C, and to the left of negative C means less than negative C. Right? So the way you're getting rid of the absolute value in this case is by writing two inequalities that can happen, one or the other. Both these are linear, so you would solve them in the same way. You subtract the constant term from both sides, and then divide both sides by the coefficient of x. Alrighty, so let's try these examples. Same sort of idea. Pay close attention to what the inequality sign is. That dictates the one of the two approaches that you're going to have to use to solve. All right, so for this guy here, it's already in a standard form. We have the absolute value of something larger than 8. That means we're going to immediately write this as two separate inequalities. The inside larger than 8 and the inside less than negative 8. Don't forget to change this sign to a negative 8, right? Otherwise, you're going to get everything satisfied, all right? And then you solve each of these inequalities like you normally would, right? All right, and so you get two rays, to the left of -2 and to the right of 10/3. We write this guy as this interval, or yeah, this interval or ray, and we write this guy as this ray. The U sign in between means union. So the solution set means, or the solution set of this inequality says that any x value that is either here or here would satisfy this. This inequality is the reverse one, right? So we have a less than or equal to 10. So we know we're going to rewrite this as a double inequality. -10 is going to be less than or equal to this stuff in the middle without the absolute value. And then that's going to be less than or equal to 10. Okay. To solve a double inequality, you subtract the constant in the middle from everything. So that would be 1. And then you divide everything by 3. That yields this double inequality here, which we write as a closed interval from -11/3 to 3. All right, so the hardest part about this is just keeping track of which of the two methods applies. Once you have that and you get rid of the absolute value correctly, you're just solving linear inequalities. All right, and then I'll let you look at these two on your own. They are very similar in nature, right? So just try these, pause it real quick, and then see what you get. All right, so if you solve those, remember this is a bigger than or equal to 1, so I'm going to write this as two separate inequalities with an or. This is a something less than 2, so I'm writing it as a double inequality. All right, and then I'll let you read the example on your own. All right, so go ahead and try these problems. They're not too bad. They're all basically the same as what we just talked about. Just make sure that when it's something a little bit more exotic, like numbers 12 and 14, let's say, just make sure you get it into the form of the absolute value of a linear expression somehow compared to a number before you launch into our methods. All right, take a look at these and let me know how it goes.